This video will cover the manufacturing technology of welding. The content includes an introduction to welding, covering both fusion and solid-state welding processes. We will also examine weld quality, including defects, inspection, and testing. Manufacturing processes involve transforming a work material closer to the desired product, adding value by changing its properties. Assembly operations, such as welding, join two or more components to create an assembly. Welding is a materials joining process that coalesces two or more parts using heat or pressure. Advantages include providing permanent, high-strength, economical, and versatile joints. Disadvantages include high labor cost, dangers due to high energy, difficulty in disassembly, and challenges in detecting quality defects. Faying surfaces are the part surfaces in contact or close proximity that are to be joined. The diagram illustrates the stages of welding, from the parts before joining to the final welded joint. There are 5 basic types of welding joints: butt joint, corner joint, lap joint, T-joint, and edge joint. These joints are defined by how the parts are positioned relative to each other. Fillet welds are used for corner, lap, and T-joints. They use filler metal to create a right triangle cross-section and are common in arc and oxy-fuel welding. Examples include single and double fillet corner, lap, and T-joint. Groove welds are primarily used with butt joints, but can be used with all joints except lap joints. Common groove shapes include square, single bevel, single V, single U, single J, and double V groove welds. Plug and slot welds are used to attach flat planes using holes or slots in the top part. The process involves filling the opening with filler metal to fuse the two parts together. Spot and seam welds are used for lap joints. Spot welds create small, fused sections and multiple are required. Seam welds create a more or less continuously fused section, often used in resistance welding. Flange welds are made on the edge of two parts, typically sheet metal or thin plate. Welding processes are classified into 2 main types: fusion welding and solid-state welding. Fusion welding uses heat to melt the base metal, often with filler metal. Solid-state welding uses pressure alone or combined with heat, and the metal is not melted. Fusion welding processes include arc, resistance, oxy-fuel gas, electron beam, and laser beam welding. Solid-state welding includes forge, cold, roll, friction, and ultrasonic welding. Applications of welding are found in construction, piping, shipbuilding, and aerospace industries. Arc welding achieves coalescence through the heat of an electric arc between an electrode and the work. The electric arc produces high temperatures, sufficient to melt any metal. Electrodes are classified as consumable or non-consumable. Consumable electrodes provide filler metal and come in the form of rods or wire. Consumable wire is advantageous as it can be continuously fed, minimizing interruptions. Non-consumable electrodes are made of tungsten and resist melting, though they are gradually depleted. If filler metal is needed, it must be supplied separately. Arc shielding protects the molten metal from reacting with air, which can degrade mechanical properties. Shielding is achieved by covering the weld area with a blanket of gas, flux, or both. Flux prevents the formation of oxides and contaminants. It melts into a liquid slag that hardens and must be removed later. Flux provides a protective atmosphere, stabilizes the arc, and reduces spattering. The quantity of heat required for welding per unit volume, U_M, is defined as K times the square of the melting point temperature T_M on the absolute scale. The rate of heat generation is expressed as R_HW equals F1 F2 IE equals U_MA_W, V equals U_MR_VW, where R_HW is the rate of heat generation in watts, and P equals IE is the power in the operation. This example calculates the power in the operation, the rate of heat generation at the weld, and the volume rate of metal welded for a gas tungsten arc welding process. Arc welding processes use either consumable or non-consumable electrodes. Consumable arc welding processes include shielded metal AW, gas metal AW, flux cord AW, and submerged AW. Shielded metal arc welding, SMAW, uses a consumable electrode coated with chemicals for flux and shielding. The heat melts the coating to provide protection, stabilize the arc, and regulate the melting rate. SMAW is highly versatile and widely used in construction and shipbuilding. However, the consumable electrode must be frequently changed, reducing arc time, and current levels require careful maintenance. Gas metal arc welding, GMAW, uses a continuous, consumable bare metal wire electrode and gas for shielding. Inert gases like argon or helium, or active gases like carbon dioxide, are used depending on the material. GMAW, also known as metal inert gas or MIG welding, produces no slag, eliminating the need for slag removal. Advantages include continuous electrode feeding, higher deposition rates, and good versatility compared to SMAW. Flux Cord Arc Welding, FCAW, is an adaptation of SMAW using a continuous consumable tubular electrode with flux in its core. FCAW can be self-shielded or gas-shielded, offering advantages similar to GMAW due to the continuous electrode feed. Submerged Arc Welding, SAW, uses a continuous, consumable bare wire electrode. Shielding is provided by a blanket of granular flux introduced from a hopper, submerging the operation and protecting the welder. The flux melts and mixes with the weld metal to remove impurities, forming slag. This process provides good protection and thermal insulation, resulting in high-quality, tough, and ductile welds. Unfused flux can be reused. Gas Tungsten Arc Welding, or GTAW, uses a non-consumable tungsten electrode and an inert gas for shielding. It's also known as tungsten inert gas, or TIG welding. GTAW can be performed with or without filler metal. Tungsten is preferred due to its high melting point. Typical shielding gases include argon, helium, or a mixture of both. GTAW produces high-quality welds with no weld spatter, and little to no post-welding cleaning is needed since no flux is used. It is commonly used for aluminum and stainless steel. Plasma Arc Welding, PAW, is a specialized form of GTAW, where a narrow plasma arc is directed at the weld area. A tungsten electrode is contained in a nozzle that focuses a high-velocity stream of inert gas. This process forms an intensely hot, high-velocity plasma arc stream. Temperatures in PAW can reach 28,000 degrees Celsius or greater due to the constriction of the arc. Applications of PAW include automobile subassemblies, metal cabinets, door and window frames, and home appliances. PAW can weld any metal, even those difficult to weld like tungsten and bronze. PAW offers good arc stability, better penetration control, high travel speeds, and excellent weld quality. However, limitations include high equipment cost and a larger torch size that may restrict access in certain joints. Revisiting the classification of welding processes, fusion welding includes arc welding, resistance welding, and oxy-fuel gas welding. Solid-state welding includes friction welding. Resistance welding, RW, is a fusion process using heat generated by electrical resistance and pressure for coalescence. It uses two opposing non-consumable electrodes and an AC power supply. RW results in a fused zone called a weld nugget. It uses no shielding gases, flux, or filler metal. While current is very high, the voltage used is relatively low. Success in resistance welding depends on both pressure and heat. Pressure forces contact between the electrodes and the work part, pressing the faying surfaces together to achieve coalescence. Advantages of RW include no filler metal, high production rates, potential for automation, lower required welder skill than arc welding, and good repeatability. Disadvantages of RW are high equipment cost and limited joint types, mostly restricted to lap joints. The two main types of RW are resistant spot welding, RSW, and resistant seam welding, RSEW. Resistant spot welding, RSW, achieves fusion at one location of a lap joint using opposing electrodes. RSW is used for joining sheet metal parts using a series of spot welds with various electrode shapes. RSW machines include rocker arm spot welders, press-type spot welders for larger work, and portable spot welding guns for large, heavy parts that are difficult to move.